My name's Kevin Pilch. I work at Microsoft on the Azure Cosmos DB team. I've worked at Microsoft for, 21 and a half years or so now. I spent the first 20 years or so working on C# and .NET, the language and the runtime and the tooling in Visual Studio, ASP.NET Core for a little while, a bunch of that stuff. So I'm an engineering manager, so I manage a group of about 30 people. So for the last year and a half, I went looking for a little bit of a change. After being a compiler guy for 20 years, I decided to see what databases are about and switched over to work on Cosmos DB. Right now, I manage our developer experience team, so the people who make the client-side SDKs that you use for interacting with Cosmos DB, the .NET one, the Java one, the JavaScript one, the Python one, the Go one, all the different languages, kind of how you interact with Cosmos DB. This is my first time giving a talk since I switched teams, so this is new material for me. So please definitely give me feedback. I'd love to kind of hear more about what I could do better talking about this subject. Moving on, let's talk, well, first of all, how many people currently use Cosmos DB in the crowd? A bunch of people. Okay, good. So this is going to talk a little bit more about kind of what our backend architecture is, how we make some of the guarantees that we talk about operate in practice. And so let's kind of jump in. We'll start with a little bit of a history of Cosmos DB. So the project started in 2010. It started when one of the Microsoft technical fellows, someone named Dharma Shukla, he was looking at how to build a cloud-native multi-tenant shared nothing database from the ground up. One of the things that is a little piece of trivia you might not know, he built an initial proof of concept of some of this while he was on vacation in Florence. And so for a long time, the project was codenamed Project Florence internally at Microsoft. So like I said, it got started in 2010. By 2014, it was already in production, powering critical services within Azure and across the rest of Microsoft. But as we got closer to launching it for public availability in 2017, we decided that we needed a better name than Document DB, which is what it had been called internally and why you still see a bunch of stuff in the resource provider and stuff like that called Document DB. So we decided to rename it to Cosmos DB to kind of reflect what our ambitions are there. And another fun piece of trivia on this, it turns out that there is already an existing product for capturing telemetry inside Microsoft that has been codenamed Cosmos for years and years and years. And so there is plenty of confusion inside Microsoft about whether people are talking about Cosmos or Cosmos DB. One is the distributed database and one is the telemetry data warehouse. Anyway. So yeah, we went public in 2017, and then we added some multi-API support for Gremlin and Cassandra in 2018. And so we're going to talk a little bit about how all those things come together. You all use Cosmos DB, so most of the rest is probably well known to you. But there's a bunch of kind of features of Cosmos DB that we tend to think about as falling into three different buckets, right? We have this kind of core extensible feature set that talks about multi-API, schema-free, automatic indexing. You know, we have a rich query language for things. All those sorts of things are kind of a core feature set. And then we have really kind of the fundamentals, the scalability, the performance, the high availability, right? We support multi-region, multi-write systems that can have up to 5 nines of availability. We support low latency with financially backed SLAs on what that means for point reads and that sort of thing. And finally, we have a bunch of enterprise-ready features. Things like, one is kind of a demonstration of faith, right? We're considered a Ring 0 Azure service. We're available in every region in Azure. Tons of other Microsoft services depend on Cosmos DB, which kind of can give you some confidence that it's a pretty reliable service. And then specific features, we have things like continuous backup with point-in-time restores. You can do private links, network isolation. You can encrypt. We always encrypt all of your data at rest with a system-managed key, but you can also bring your own key so that we don't have access to what the key is, so that everything is always encrypted. and things like role-based access control and so on. So I've kind of mentioned already some Microsoft services using Cosmos DB, but who else uses it, and what's scale kind of like? Here's an example of some of the customers that we have, some people who are using Cosmos DB at scale. You might have heard of some of those companies down there and some of the products within Microsoft. So Microsoft Entra, Azure DNS, Microsoft Teams, et cetera. Companies like Walmart, ChatGPT's chat history is kind of stored in Cosmos DB now. Talking about scale, that second bullet point, we have a single customer who operates at the scale of 100 million requests per second over petabytes of storage with their data available in over 40 regions, right? And so, that's one of our customers. It's not kind of the entirety of the service we provide. So how do we go about doing that? Let's talk first about kind of a very high-level architecture. So how do different requests operate in Cosmos DB? This is a pretty simple diagram, but we have a bunch of back-end storage replicas, storage nodes we call them, right? And in between that and the customer, there's kind of the Azure cloud, where typically you're running VMs or containers or Kubernetes pods or whatever. And from there, typically you reach out and you talk to this Cosmos DB API gateway. And the API gateway sits between your application and the backend storage nodes. And that's really one of the ways that we leverage or that we enable this multi-API support. The gateway is able to build up a query, do the translation from the API-specific semantics to our backend semantics, distribute the query across all the backend nodes, aggregate the results, and finally return those results to the user. We'll talk a little bit more about what that gateway looks like later, but first let's dive into kind of what the backend storage engines look like and how they provide some of those availability guarantees that we talked about. So again, probably review for most of you who already use Cosmos DB, but let's talk about the resource hierarchy a little bit, right? We have the idea of an account. This is like and then within an account, you can have multiple databases, and within a database, you can have multiple containers. Containers are provisioned with the idea of these resource units, right? This is how you decide how much you want to pay us, and how much traffic you think you're going to have. It's also how we know how much capacity to reserve for you so that we can ensure that we meet those resources. And then kind of each operation that you do consumes some of those resources from the container. And finally, the way that we do horizontal scaling is through this idea of partitioning. So we partition your container through this idea of a partition key. It's like a shard key in most other things. And they can be either a single partition, or they can be hierarchical, or they can be composite for things like the Cassandra API. Let's talk a little bit about kind of what one of those might look like. So there's this idea of a difference between a logical partition and a physical partition. So when we're talking about the backend storage, we often talk about physical partitions, although in a lot of ways they're kind of an implementation detail, or they're supposed to be an implementation detail as far as customers are concerned. But a lot of times kind of the performance implications of multiple physical partitions can come to bear in your application. And so we'll talk about that a little bit. So let's imagine, we have a partition key that is based on the city property. And from that, we can route data to different backend storage nodes. And so this has an example where Seattle and London, they're different logical partitions, right? They have different values of the partition key, but they might get routed to the same physical partition. They might end up on the same actual backend storage partition. Partitioning, it's great for horizontal scale, right? It's how we actually are able to distribute this data and provide these guarantees, but it comes with some complications, right? In data modeling, it's important to do a good job of figuring out what your partition key is going to be. You can run into problems like what we call hot partitions, right, where most of your reads and writes all go to the same partition key, which means that even though you provision a bunch of capacity, that capacity is kind of evenly distributed among each of your partitions. And so if everything ends up going to the same partition anyways, then you have a hard time scaling. On the reverse side, a lot of people get around that. They say, well, great, I'll use a GUID or a random number or something like that for my partition key. You get good distribution of your data across all of your partitions. But if you want to use the rich querying facilities that we have, that means that that query then has to distribute across every single one of those partitions and collect the results. And so there's often, one of the challenging parts about working with a horizontally scalable system like this is doing a good job of picking the partition key. We have some features to help alleviate some of these. So we have this idea of hierarchical partitioning can help with some of this hot partition. Actually, it can help with hot partitions. It can also help by trying to group related different partitions together in the same physical partition so that those cross-partition queries are a little bit less expensive. So if this is something that you've been running into, I would suggest taking a look at this idea of hierarchical partitioning. Moving on, let's talk a little bit about replicas and partitions. I've talked a little bit about it so far, but this idea, the terminology that we use all the time, replica sets and partition sets, replicas and partitions, what's kind of the difference? What do they look like? Well, a replica set is the set of replicas for a given piece of data within a single region. And so typically in Cosmos DB, we'll have 4 replicas of every piece of data that you store, and we're going to get into the details of how that's laid out a little bit in the next slide. But kind of each region, each partition of your data, each piece of your data is stored in 4 replicas. One of those on the slide is called leader. Sometimes we call it primary, sometimes we call it write. But basically each replica set has one copy that is the master copy where all the writes happen, and then it has a variety of secondary replicas or followers or read replicas, we call them. And then if you have a multi-region account, that data is also replicated in each different region. And so within each region, you have kind of one of those copies of a replica set. So you'll have 4 independent stored copies of your data in each region that the data lives in. And so let's dig into that a little bit more. So this is kind of a representation of what this looks like inside a data center for us. We have this idea of fault domains in Azure. And so it's the idea that within a data center, something can happen to one machine. It shouldn't necessarily impact other machines within the same data center. And so typically this is stuff like machines are guaranteed to be in different racks or on different power systems or that sort of thing. And so one of the things that we do is we distribute each of those replicas across different fault domains. And each machine can host multiple customer pieces of data. And so the right example there, or the left example with the red arrow, you can imagine partition 1 for one customer is spread across multiple different fault domains, right? And then you can imagine for a given customer, the different partitions are spread among different clusters. That kind of spreading among different clusters is how we get the elasticity and the scale, and the spreading across different fault domains for a given partition, for a given set of replicas, is how we get some of the durability and availability that we talk about. One thing that's kind of an additional point here is you can get even better availability with the idea of availability zones, which is kind of a relatively new concept in Azure. And this is the idea of like an even more independent sub-region within a region. So you can imagine kind of two buildings across the street from each other might be different availability zones. And so even if something happens to one of the buildings, if your data is replicated across the two availability zones, if some of your replicas are in each of the two different availability zones, you can still be available even though part of that region has gone down. I'm not going to talk much more anymore about availability zones, but that's something else to kind of think about there. Any questions so far? Am I going too fast, too slow? Is it making sense? Yep.
No. So we have software updates for component, but if you bring out a security fix and then you roll that out across every single domain at the same time, it's just a problem with it. It takes everything down.
Yeah, well, we're going to talk about that in a little bit. Yeah. All right. Let's look next at kind of what the request flow looks like for a document write. How do we preserve kind of the semantics that you think about what's inside one of these replicas? So a single backend replica, actually let's talk about the kind of contents of a backend replica. What do we have in there? So we have a B tree. We have an inverted index. This is kind of used for query terms, the index query terms. That's a B+ tree. There's a really interesting paper about how that indexing works. There's a link there. I'll copy it to the resources section at the end. Honestly, kind of some of the lock-free code for building that inverted index, someone could probably, not me, because I'm not an expert in it, but someone could probably do an hour-long talk in kind of just how that B+ tree inverted index works. But needless to say, it's kind of an important part of what powers our indexing and queryability within Cosmos DB. And then we have the query engine. This is kind of, going back to my compiler days. You write a query in our NoSQL language. It gets translated into query IL. The query engine has a little virtual machine that knows how to interpret that IL and filter the results and do projections and all of that stuff. And so that lives in each one of our backend replicas. And then finally, we have a replication queue. This is like a log of writes that happen, and we'll talk about what that's used for in a second. So what does it look like when you write a single document? What happens? So you've got the secondary replicas, right, and a primary replica. So we talked about this idea of primary, secondary, also write replica, read replicas. So writing a document, the first thing that happens is the primary replica kind of collects a package of data about that, gets ready to commit it, but it doesn't actually commit it into its storage yet. First, it packages all that up, and it distributes it to each of its secondary replicas concurrently. Each of the secondary replicas takes that, commits it to its storage, its index, and its replication queue, and then acknowledges the result back. Meanwhile, the primary replica, the write replica, waits until it has a quorum of the read replicas acknowledged before it actually commits the transaction. And so this way, knowing that one is that this is the primary replica means that it doesn't actually reflect the results until we know that at least two other replicas have stored that data and acknowledged it back. And then it commits and returns to the user. The replication queue is there for the cases where that third replica didn't actually acknowledge the write. The replication queue can be used to get that other replica up to date later on. But this is kind of how we get some of those consistent results across writes, because you're guaranteed that before control returns to the user for a write, it's present in the write region or the write replica and at least two of the read replicas. So 3 out of the 4 replicas are guaranteed to have the data committed to disk, flushed to disk, before that write document ends up returning. Make sense? All right. So this is the 2 replies coming back. Then we write flush everything. Always forget that I have a builder slide for this. Then we commit everything on the write replica. All right, so then what happens if we're talking about multiple regions? Right, that was all for within a single region. There's 4 replicas in a single region. So what happens when I have multiple regions? Well, the first thing that happens is the same thing that happened in the last case, right? Client issues a write, the write goes to the primary issues it to each of the secondaries. One of the secondaries is designated as the forwarder or the replication secondary. And so that one secondary, on your behalf, issues a write to the other region. And then, because one of the features that Cosmos DB supports is the idea of multiple write regions, of course, the same thing can happen in the other region. So a client in region B can do the same thing, and of course, the whole process flows in reverse. Yes?
Slightly earlier than you saying, if none of the secondaries acknowledge receiving and committing the data, does the primary then not commit it either?
The primary will not commit it if it doesn't, yeah, that's correct.
It says to the user you failed to store it. It doesn't, so what would be wrong if it did try to commit it and then try to store it to the primary again?
The problem is if first I'll repeat the question. What happens if 2 of the read replicas don't acknowledge that they've written a write? So let's go back over here. Great question. So what happens if only one acknowledges the write, or 0 of them acknowledge the write? Well, if you return to the customer and say, I've written that data, fine. What happens if the reason why those 2 didn't acknowledge the write is because something is happening and the data and power is failing in that data center? And so those 2 machines are down. Your idea is, well, we've got the replication log, we'll hold on to it and we'll catch them up later. Well, what if we crash at exactly that point as well, right? Then you've told the customer, you've returned to the customer, hey, I've written your data, it's safe, you can trust me, but it's actually not on any of the machines that exist, right? And so when power comes back up, that data's gone, right? And so this idea of having a quorum, having it be on multiple machines flush to disk is one of the ways that we provide the consistency guarantees that I was talking about. Does that make sense? Great. Okay. So, multi-region writes. Things can go in reverse. 2 people can write the same document. Turns out getting time right across the internet, if we didn't allow for multiple people to write the same document across the internet, that wouldn't be a very useful system. But what this can mean is that as that secondary is replicating the data back to region A, someone else may have already written the data in region A. And so what do we do in that case? Right, somebody says we do conflict resolution, right. So we have this idea of conflict resolution. We have tunable ways we can do that. Each document has a timestamp field within it, and so you can say whoever wrote to it last wins. You can populate a stored procedure to run whenever a conflict happens that can decide how to deal with the results. You can have it pop into a queue to be dealt with later. Or, there's some API-specific things Cassandra does, like per property conflict resolution with timestamps per property and that sort of thing. So there's kind of a variety of different ways. But it is something you have to think about if you're going to have a multi-region, multi-write region account. Often this doesn't come up very much because a lot of the time people kind of focus the writes on the nearest region to where the customer is. And so often, like if your partition key is by customer or by region or something like that, then you're unlikely to have multiple people in different regions writing to the same document, but it is something that we have to be prepared to deal with. So those are writes. Every write that happens in Cosmos DB is consistently written to the database before it's acknowledged, before you get a success back from the API call. But that's not necessarily true of reads. For reads, we offer 5 variations of consistency models. So first of all, you can set a default for each account, each container, and then on every read request, you can choose to have a different one if you need to for that particular read request. There's a trade-off in these between latency, availability, and throughput, right? Latency is a great example. If I say that I want globally strongly consistent reads, then that means every time I issue a write, I can't read from that database until that has been replicated to all the other regions that are part of my account, and all those other regions have confirmed back to the region that you're doing the read from that everything is there, right? So that obviously implies at least a cross-region round trip as part of your latency for every read that you do, right? And so, like I said, so moving from the left of the slide, globally strong means every write shows up in every read across the world, right? And then you can get down to bounded staleness, which is typically the best way to think of it is it's consistent within a region, right? So within a region, every time you write something, every read after that is going to see it, and there's kind of the bounded part of it is, and don't let me do any more writes if the replication to other regions have fallen too far behind, right? If it takes more than 10 minutes to replicate to other regions, then maybe slow down my ability to write to this region so that I don't get too far out of date and have an issue if this region goes down where I have lost data again, that sort of thing, right? Session, this is kind of our most common, this is the default consistency level. This is the idea that if I, on my machine, write something and then I issue a read, I can see the thing I just wrote, right? That's pretty convenient. It's pretty hard to deal with some of the ones to the right around eventual consistency if you have this model where you need to be able to look up something after you wrote it, right? If you can't guarantee that you see it right after you wrote it, that's a programming problem that is hard for a lot of people to wrap their head around. Unless you're doing, queuing type things where you actually don't need to write it from the same machine as long as it shows up at some point, right? And so there's different use cases for all of these different consistency levels. And like I said, it's kind of a trade-off among your latency, your availability, your throughput. The one I didn't put on the slide is, like I said, your comprehensibility of the problem space, right? Globally strong is easy to understand. It's like the way we tend to think about databases a lot of the time, right? Once I write something to the database, it's there, every read, it shows up. But it's pretty expensive. And so for a lot of problem spaces, we want to be able to slide down further down to the right on this scale of consistency. Just wanted to highlight, again, this has nothing to do with writes, right? Like a write to a given replica is entirely consistent before it returns to the customer, right? Does that make sense? Okay. I said entirely consistent, but that's actually not necessarily true. It's consistent with at least 2 of the reads, right? So 3 of the 4 replicas are consistent, but that's how you can get eventual consistency where even if you read from one of the secondaries, you may not see the write that you just did. So let's talk about this a little bit. Reads with tunable consistency. How is this implemented on our side? It's not super complicated, right? If you do an eventual or session consistency read, we pick a read replica at random. It's not quite at random, but close enough. And we issue a read to it, and we give you the data that's there. We check the session token if in session consistency, but basically we read from one of your read replicas. On the other hand, if you do bounded staleness or strong, we pick any two. And we only return the result if there's a quorum between those two, if they agree on what the value that you're trying to read is. Because we know that a write is guaranteed to be in at least two of the three read replicas before the write finishes, we know that if we read from two of those read replicas and they agree on the result, that they have the latest result. If they don't agree, then maybe we got one that is behind, right? And so then what my team does in the SDK is it might have to reach out to the third replica and ask it, hey, have you seen this or not, right? And so this is how the SDK handles quorum, right? Questions? Does this make sense? Yep.
Does that mean that the bounded consistency is going to be more expensive in terms of IUs?
Yes. So again, question is, does this mean that global strong or bounded staleness is going to be more expensive in terms of RUs? The answer is yes. It will, we say typically a point read of a 1K document is 1 RU. A point read in strong consistency is 2 to 3 RUs, definitely. Any other questions? All right, we're moving along. Ensuring high availability. So this is going to get into some of those upgrade questions, kind of what happens as we're doing upgrades, but not just what happens as we're doing upgrades, what happens with machine failures and hard drive failures and all of those things, right? Like one of the reasons why we want to have 4 replicas of your data is we want it to be highly available, we want it to be durable, right? We want to give you back the results that you've written. And I mentioned earlier kind of the scale that we're running at, right? However many million requests per second across petabytes of data. All of that data, as we're going to talk about in a little bit, is stored on directly connected live SSDs to machines in data centers. You can imagine how many SSDs that is, and given the failure rate of SSDs, you can imagine that sometimes one of these replicas has an SSD fail, or sometimes the power goes out, or sometimes we need to take a machine down to run upgrades on it. And so how do we deal with that case? Well, we have kind of pretty robust monitoring of all the systems. They all kind of send health checks back to our coordinator systems. They report a bunch of different metrics about how they're doing, what the disk queue length is, what the memory usage is, all those sorts of things. And our central system can decide that secondary is no longer available. So let me find a machine that has capacity, and I will just build a new secondary. So I'll basically copy the data from the primary and give it to the secondary. And what happens during that time depends on the consistency level you've chosen and all of that sort of thing. But because we know that the data is on the right region, or the right replica, we know that we can copy it. And it's on at least one of the other read replicas, right? That's going to be important in a second. So basically, we transparently to you bring up a new machine with the data on it. We copy the partition over and bring it up. And this is done kind of live with the replication log, replication queue. So by the time the machine is available, you don't see any impact to your application. Any impact to your application. The reality is, what you typically see, if you're looking at all of your requests and you're looking at kind of the metrics of what's happening, you'll see a response come back with something like a 409, or a 410 gone response, right? And that's an indication of a gracefully shutting down replica. It says, I don't have your data anymore, it's gone. And so in that case, the SDK we're going to get to this flow in a little bit, but it'll go back to a central system and say, hey, where's the data for this partition? And it'll get a new address and it'll try on that other address. And so what you'll actually see is some impact to your latency because your request will fail and you'll have to go try on a different partition somewhere, right? So you might see some failure network calls. That's by design. It's part of building a resilient distributed system. Okay, what happens if the write, the storage primary goes out? Well, in that case, we use something called Paxos. This is kind of a well-researched, well-documented algorithm in the distributed systems space for electing a new leader. And so we take the 3 remaining read replicas and say, let's elect a leader among those 3. I'm not going to explain all of the details of Paxos. It's complicated. I will just say we'll pick a new leader, and then we will follow the same process that we did before to pull in another secondary and copy the data to it. So we will again have a write and 3 reads. Part of the Paxos implementation guarantees that the winner of the election has the latest writes that have been told back to customers, right? So again, if one of those other read regions hasn't acknowledged the write yet, hasn't caught up from the replication, then it will not be elected the leader, and so you don't have this kind of write ahead problem. So that's something that we had to deal with, so that you don't have to deal with that. Yes.
If you have a lot of the write requests coming in, will they take a break from new write until they elect the new leader?
It's like you're a plant. So the question is, what happens if a lot of write requests are coming in? Will they take a break? How do we handle kind of load scenarios like that? And the answer is this is kind of baked into our RU philosophy, right? And so we have this idea of resource governance. And so the idea of resource governance is that when a request comes into our backend, we decide whether we have the capacity to deal with it or not. Right? And typically, the way we measure whether we have the capacity or not is by those request units that we talked about at the beginning. And so for simple CRUD requests like reads and writes, that sort of thing, we will we know ahead of time how much those are going to cost. And so we just don't let a request start if we're already out of capacity. And so to your point, your question was kind of like, what happens if there's a lot of writes happening at the time while we're electing a new leader, right? Well, electing the new leader will typically happen during one of those write requests, right? Like that one write request will either time out or by the time it'll wait until we've elected a new leader, right? And from then, those requests will continue. They might have slightly higher latency as we're doing more work on the machine to replicate to the other read replicas, but they'll continue. So typically we won't block requests in that case, unless you start sending a lot of requests, in which case our capacity gets overloaded. We get to your limit of request units, what you've provisioned, and then we typically return a 429 retry later result that says, come back in a second and a half or so. So I guess there's 2 things that can happen, right? So I mentioned kind of point operations. CRUD operations are pretty simple. We know how much they're going to cost. The thing where we don't know what it's going to cost is queries. And so the whole query VM that I talked about with queries, we'll typically start running a query. And within the query VM, as it's chugging through collecting results, it'll periodically check and say, how many RUs have I used? Is it more than I was given as a budget at the start? And if it is, it will do one of 2 things. It'll either return a successful query with partial results, with a continuation token that says, hey, here's the results I've got so far. I'm out of time to calculate more results for you. come back later with this continuation token, and we can continue from where we were, right? That's if you get kind of close to your capacity. There's also cases where you can write queries. For example, if they happen to not use the index, like if you tune your index and remove something from it, and we end up having to load every document and scan through all the properties of every document, those can be very expensive queries. So you can churn through kind of all of your RU budget very quickly. In those cases, you'll end up with this kind of 429 where we say, actually, you didn't even just use this 1 second's budget, you used the next 5 seconds budget. So come back and try that query again in 5 seconds when I have some time to handle it. Right? Does that make sense? So that's this idea of request units. And this is kind of a key part of how we manage to build a multi-tenant system. Right? One of the big problems in multi-tenant systems like ours is, I said at the beginning, one physical machine might have a bunch of different customers' partitions on them, right? And one thing you don't want as a customer with your data on that partition is for your neighbor to run an expensive query and have that expensive query bring that server to its knees and mean that your queries start taking longer, having it impact your latency, right? And this is one of the reasons why those request units are so important for us, is because we have this idea of resource governance, right? We know that a given machine can handle n 100,000, n million RUs, right? And so we know how many customers we can put on it. If every customer has 1,000 RUs, and a machine can handle 100,000 RUs, then we can put 100 customers on that machine, and as long as we actually stop running the results when a customer exceeds its budget of RUs, we know that we can maintain our SLAs for every other customer with that machine. And so this is why we kind of throttle, it's why we have all of this RU, it's why we normalize everything to RUs, is so that we can have this RU capacity planning for us, and resource governance. Does that make sense? Great. Whew. I was worried at the beginning we were going pretty fast, but we're slowing down, so that's good. Elasticity. So we're going to talk more about what I was just kind of talking about, this idea of provision throughput and elasticity. So we have a variety of different models because customers have a variety of different types of traffic. Right? Many products say Teams, right? Teams uses us, stores all of the chat history in Microsoft Teams is stored in Cosmos DB. It turns out that Teams has a kind of follow the sun model, right? Most people use Teams during their workday. And so if you look around the world at our transactions from Teams, they go, in the US during one period of time, then they are writing in a different region during a different period of time, right? And so people want to be able to have different ways of provisioning the system depending on their usage patterns. Sometimes things happen in batch, right? So, maybe one account doesn't do very much during the week, but every weekend it goes and, does a big batch job, or every night at 2 a.m. does a big batch job, right? And so you want to be able to have different provisioning for different things like this. And so we offer 2 simple ones, right? Provisioned, right? We offer you provisioned. We guarantee that you can use 30,000 RUs, right? And we pay you a fixed cost. You pay us a fixed cost. We don't pay you. That'd be nice for you if we did. You pay us a fixed cost for those 30,000 RUs, right? And the way the math breaks down for us is we give you 1 physical partition for every 10,000 RUs that you have provisioned. And so that's fine if you have a steady workload, right? That kind of continuously is using that amount of data. The second is this idea of auto-scaling throughput, right? And so you can say, well, my workload is going to use somewhere between 1,500 and 15,000 RUs, but it depends. It's variable, right? And so in that case, we kind of provision you up to what the maximum of that is, number of physical partitions, but we charge you for what the peak number of RUs you used in any given hour is. So for each 24-hour period, we pick the second within that period that had the highest number of RUs, and that's what you get billed for that hour, right? So if you have a spiky workload, this can be a way to save a lot of money because most of the time you're kind of sitting at that idle lower level, and then when you have a spike, we can instantly scale up to that level because we've already actually provisioned you the machine resources to do it, and you pay for the spiky workload when you have the spiky workload. Make sense? Not shown on this slide, we also have a serverless model where you actually just pay for consumption, right? You pay each time an RU happens, you pay per RU. And so if you have a very low usage workload, occasional workload, that can be better than provisioning ahead of time what the RU budget is going to be. It does mean, you have somewhat less control over instantly scaling to a large number of RUs, and so it's something to think about whether you want to use serverless or not. But it's great for getting started, small projects, experimentations, that sort of thing. Or, like I said, kind of those really occasional workloads. And then the last thing I'll mention, new in preview, we announced at Ignite. We are also now offering this auto-scale idea, but auto-scaling per partition or per region. So instead of saying I want to scale my whole account in every region, I can say, actually, I know that this region is busy right now, and actually, I even know that this partition key within that region is super busy, so I'll pay more for that one to have better provisioning, right? So that's kind of a new feature. So a lot of flexibility in kind of how you provision things. But what does it actually look like? How do we manage elastic scaling in the case where you don't have the capacity already? So let's imagine you have a container that's provisioned with 30,000 RUs. Like I said before, that means you'll get 3 physical partitions, each of which is able to serve 10,000 RUs. And then you decide to bump it to 60,000 RUs. What do? Well, the reason why we say this can take a little bit is because we go find 6 places to put partitions, and we copy the data from your 3 partitions into 6 partitions. So we do a bunch of work to kind of optimally split these so that half your data from each partition goes into one of the partitions below. We copy everything. Once we finish copying, we go through the replication queue, and we copy down everything until we're at a point where it's live, and then we update the containers topology to say, hey, forget about those old replicas. These are the replicas now. And this is another case where, like I was saying before, you would get one of those 410 gone exceptions or 410 gone responses because now those old replicas are gone because they were at a lower capacity, and we want you to redirect and use the ones with higher capacity. Does that make sense to everybody? So no downtime happens as part of this. This slide, for simplicity, showed kind of the 3 initial replicas going away all at the same time. That doesn't actually happen. As soon as the copying's done for a given pair beneath it, we'll update the topology for each of those other containers at a time, right? In a 3 to 6 partition split, that's less interesting. In our customers that have got hundreds or thousands of partitions, if you had to wait for every partition within 1,000 to split, that would be a big deal, right? And so the fact that you can split individual partitions is important. All right, we're going to fly through some of the rest of this stuff. Multi-API support. I said we come back to this, right? We support multiple APIs. The best thing about Cosmos DB and the best thing about the rest of this talk, the reason why I can fly through it, is that everything that I've talked about so far applies to all of our different APIs, right? All of our different RU-based APIs, right? The idea is they all share everything that I just talked about. So when we make investments in any of those things that we talked about, they benefit all of our APIs. It also means, we don't have to think about all of those durability and availability decisions for every one of the APIs that we do. It means that if we optimize something, it gets optimized for all of them. And then, so sometimes, the NoSQL backend, which is kind of the default one, sometimes it doesn't have a feature that is needed to support one of these APIs. And so the idea there is we build extensibility hooks into that backend to allow us to support the APIs rather than duplicating a bunch of code and stuff like that. It's, just sound engineering, but it's worth pointing out. So back to this slide that we saw before. Each of these is kind of an idea of a set of microservices, right? For each API, we have a microservice, and those run on those compute gateways. And again, we have to kind of think about this idea of blast radius and noisy neighbors and how we maintain throughput and availability for those. It's a difficult space to build this compute gateway and to build it well in a multi-tenant way and to build it cheaply. It's currently super expensive for us to run the API gateway, and so working on ways to improve that, definitely. And so we'll talk a little bit about that. So one of the things that we want to do there is we want to make sure that we have flexibility in scaling it. So I talked about all those fault domains and clusters and stuff like that. When we deploy the API gateway, we can do that independently of any of the back-end deployments and scale them independently of each other. So depending on how many people are using multi-API stuff, we can choose to how we want to scale it. That shared platform layer, like I said, both in the back-end and then within a compute gateway, we kind of try to normalize stuff into one platform layer so that we can optimize it once for all the different APIs. Resource governance is a challenging problem with these API gateways. It's very hard to know how difficult it's going to be to translate a Mongo query into a NoSQL query and back ahead of time. And so it's hard to figure out exactly what on the API gateway is going to end up being a noisy neighbor problem. And so typically today we do that through load balancing rather than through direct resource governance like with the RU budgets that we talked about in the back end. And finally, we do tie things pretty tightly to the underlying hardware. So we'll talk about this in the next slide, but like we use NUMA boundaries and processor affinity and that sort of thing. So you can imagine the way that this compute gateway, API gateway works is a bunch of small processes, one process for each API that we might be doing, or multiple copies of the same process for each API to scale. We run on large machines in Azure, so those are often multiple socket machines, and so they have multiple NUMA nodes. NUMA, for those who aren't aware, is non-uniform memory access. It's when you have a computer where, depending on where your process is running, it can take different amounts of time to access different parts of memory, right? And to synchronize memory between different threads and that sort of thing. And so we do a bunch of work to kind of make small processes that can run on a small number of cores, and then we affinitize them to those cores so they don't have to cross any of those boundaries and do those expensive calls. We also do a bunch of work kind of optimizing the process itself that we'll talk about in a second. But I mentioned before load balancing. We have multiple levels of load balancing to deal with this idea of noisy neighbors and if something goes wrong on one node, to be able to kind of contain it to that one node. So within a given VM, we even can reroute connections between different processes, right? We have the Azure SLB does load balancing. We tell it to take VMs out of rotation if they get busy, right? So some customer picks a crazy random query that makes the CPU spin up. The Azure SLB will take it out of rotation, right, and not route anything else to it. We also are able to, like, at our level through monitoring, say, hey, this cluster is getting very busy. Let's take all the requests from this given account from now on and put them into a different cluster so that this cluster can cool down. And then finally, this kind of work in progress, we're working on a more active load balancing where we can kind of look at live health data from all of the different nodes, pick the best one. We've got some interesting prototypes using historical insight and ML models of what traffic is likely to do for a given cluster and do load balancing there. Finally, system performance. We talked a bunch about kind of the back end before and what we do to optimize across the whole back end. It's super important. We have a bunch of check-in gates in Azure DevOps that run performance tests on every check-in. Even a regression of less than 1% in any of our benchmarks is not allowed to be merged into our code base. And so oftentimes people have to go find somewhere else to optimize if they need to do some more logic for a given operation, right? And so we kind of hold ourselves to a consistently high bar around performance, but it is something that has to be kind of designed for and enforced and thought about, and it's an entire culture to build a highly performant system like this. On the API gateway itself, I should have mentioned all the backend stuff just about that I've talked about is written in C++. The API gateway is written in .NET, either .NET 6 or .NET 8. It was .NET 6, but I saw the PR for .NET 8, so I haven't checked my mail today. If it got merged, then maybe it's running on .NET 8 now. We work closely with the .NET team. I said I spent 20 years in the .NET team. Various other people on the team also came from the .NET team, and so we work closely with them both to provide data about where they could help us, but also for them to help us tune and optimize things. So we work hard to do a good job there. Let's see what else I wanted to talk about. I think that's the main things I wanted to talk about. Does anyone have any questions for the last 2 minutes? Yes?
You mentioned that the SDK also does a lot of heavy lifting in terms of selecting the replica to make the call for. What is the rough... can you talk more about what the SDK part of this?
Sure. Conveniently, it's my next slide. Wow. You guys are doing a great job of asking me the questions that I want to answer. So for those of you who are using the .NET SDK, you may have seen that we have this idea of connection mode, direct connection versus gateway connection. The direct connection mode basically allows you to skip talking to the routing gateway for most of your operations. And so what the SDK actually does is the first time you make an operation, it will call into what we call the routing gateway and say, hey, I need to get some data, but I don't know where any of the data lives. So for this account, can you give me the topology? Can you tell me where all the backend replicas are for each partition key range? What's the address? What's the port for all the different replicas? And then it can directly connect to those backend replicas. So we do that over a custom TCP protocol with custom TCP serialization. It makes it difficult for firewall administrators because we can reach out on any random port. It makes it difficult because we connect to all 4 replicas for each partition. And so the number of outbound network connections that we can make can be huge. I also talked at the beginning about cross-partition queries. You notice everything we talked about today with the backend nodes was one partition, right? And so the other thing the SDKs have to do when they're in this direct mode is like stitch together all the results across all those different partitions. If I say like select something and order by some field, right? Well, that order by can only happen on the client as part of the SDK, right? So a bunch of that logic ends up having to happen in the SDK. Does that kind of answer your question? Does that help? So I mentioned before, all those kind of gone exceptions, that sort of thing, they kind of re-trigger this flow. If you try to read from a read replica, you get a gone exception, they re-trigger the SDK to go ask for new topology information. In the .NET SDK, we also do it implicitly every 5 minutes, just in case, to try to preempt the idea of the topology changing. We kind of reach out and say, hey, has anything changed in the last 5 minutes? Have any of my partitions moved around? But the reason why I have a team as big as I do is because a bunch of this stuff ends up having to happen directly in the SDK, and with 5 and maybe soon to be 6 or 7 languages to support, there's a lot of work to support those things in the SDK. All right, I think we are 1 minute over. I want to thank everyone very, very much. This has been a great talk. I have some information here, pointers to docs and that sort of thing. Please feel free to reach out to me on Twitter. I'm at Pilchy, threads, pilchy.dev. Somebody had already taken my handle. You can email me. It's kevinpi@microsoft.com. Definitely feel free to reach out if you have any questions. All right, thanks a lot.